All right, welcome back. So today, let's get the dimensions of these physical quantities. Let's see how their dimensions are gotten. All right, so first, let's go straight up. We have force. So let's just indicate force with F. Force is mass times acceleration due to gravity, right? So first off, we need to know the dimension of acceleration. Acceleration is velocity over time, right? Right? Yes. Now, remember in our previous videos, we have already gotten the dimension of velocity to be lt raised power minus 1. Dimension of time is, of course, t. So at the end of the day, this is lt raised power minus 2. So the dimension of acceleration is lt raised power minus 2. This is just simple indices. Now, that being done, I come back again. F is equals to m times a. So dimension of mass is capital M, right? Times dimension of acceleration, which is LT raised to power minus 2. So at the end of the day, we have M LT raised to power minus 2. So this is the dimension of force. Easy. Now, let's solve for the dimension of pressure. Pressure is simply force over area, or you say force per unit area. Now, what is the dimension of force? M LT raised to power minus 2. What is the dimension of area? Already we've solved the dimension of area to be L square. So one L takes off one L. So at the end of the day, we have M T raised to power minus 2 all over L, right? Because one L is still remaining. So that, according to indices, is the same thing as M L raised to power minus 1 T raised to power what? Minus 2. You might be asking, how did this L change to minus 1? Remember, this M T raised to power minus 2 over L is the same thing as M T raised to power minus 2 times 1 over L. And according to indices, 1 over L is the same thing as L raised to power minus 1. So that is how we got this. Remember, 1 over L is the same thing as L raised to power minus 1. If you don't know, know now. Anything, this is the same thing as 1 over A, according to indices. So that's what we did, and we got the dimension for pressure. Easy. Now, I need to clean the board so we can solve for the other quantities. All right, let's go. So now the dimension for moments. Class, what is moments? Moment is simply force times perpendicular distance. So what is force? The dimension of force is m L T raised to power minus 2. Dimension of distance is L. So at the end of the day, we have m L square, sorry, T raised to power minus 2. Correct. So that's dimension of moment. So we'll move to dimension of work done. The same thing. Work done is force times distance, right? So this is simply m L T raised to power minus 2 times L. Of course, it's going to give us the same. So it is safe to say that work done is dimensionally equivalent to moment. Dimensionally equivalent to moment. So put that in your head. So the last one, which is power. Power is simply work done divided by time. So what is work done? Dimension is m L squared T raised to power what? Minus 2, just like we've got in here, over time is just t. So this is the same thing as saying m L squared T raised to power minus 3. That's the dimension for power. As simple as ABC. Now, this knowledge of being able to derive the dimension of any quantity in the world of science is very, very handy, because you will use it when you start doing what we call dimensional analysis, and that's more like applications of your knowledge of dimensions. So you will now start using this knowledge of dimension to check the correctness of a physical equation. You use it to establish a relationship between two or more physical quantities. You also use it to derive the units of physical quantities, provided you don't know their units. Because, come on, from this dimension, I can get the unit, the derived unit of power without any problem. It's gonna be that easy. So, yeah, see you in the next video. When we talk about dimensional analysis and the applications of dimensions.